Okay, so we've seen now the equilibrium for the Solow model. It's given by the point of intersection of those two lines, where one is investment per worker and the other is sort of the amount of capital per worker we're losing to depreciation and population growth. So now we're going to do some experiments, right? So remember that when I talk about experiments, or often when economists talk about experiments, they don't mean, experiments like you'd see in science, but rather let's change some parameters in the model. Let's change some exogenous variables and see what effect it's going to have on the endogenous variables. Now, recall that Solow's criticism of Herod-Domar is the following. This is from the earlier slide. It says, were the magnitudes of key parameters, so for example, the savings ratio, the capital output ratio, the rate of increase of the labor force, okay, any of these, if they were to slip ever so slightly from dead center, from this knife edge we talked about, the consequence would be either growing unemployment or prolonged inflation. So a question we might ask then is, well, what about in this model? What if we change any of those parameters? Okay, are we going to see this instability that we see in Herod-Domar? So in particular, let's start with an increase in the savings rate, S. Okay, let's look and see what happens here. So imagine we're initially in equilibrium. So remember, the equilibrium is given by the following condition. And we're initially at savings rate S subscript 0. Okay? Now, an increase in savings, so if we increase this S, the savings rate, is going to lead this left-hand side to exceed the right-hand side. Okay, so let's say that S goes up to S1. S1 is greater than S0. Now we're going to have this left-hand side is greater than the right-hand side at our former equilibrium value of K star. Okay? So what does that mean? Well, remember we saw this just means that there's going to be a growth in per worker capital. Okay? And because the growth in per worker capital is given by this equation, and now it's greater than 0, simply because this term is greater than that one. Okay? So that means that capital is going to grow. Fair enough. So let's look at this then, graphically, what this looks like. So an increase in the savings rate shifts up this curve, right? And you can see immediately what this means, right? So at our former equilibrium, now we have that savings, or the addition to investment, or the addition to the per worker capital stock, is now greater than the amount we're losing to depreciation and population growth. And therefore, K, little k, will increase up until our new equilibrium value, K double star. Okay? So what happens is that we'll now have a new equilibrium value where little k, capital per worker, is higher. Okay? And this is what I've written here. And notice in particular, this is a new steady state. This is a new stable equilibrium. Capital increases up to a point and then it stops. Okay, so we don't have this knife edge problem where suddenly if we change one parameter, suddenly everything becomes unstable. Okay? Rather, we change savings and we just slowly move to this new equilibrium value of capital per worker. And notice also that because y, or little y, output per worker, is just a function of little k, a positive function, now that we have more capital per worker, we also have more output per worker. Okay, so both little k and little y have increased. So, notice here I said that this is stable and that we just migrate to this new stable equilibrium. So why is that? Why doesn't k keep growing? And the answer is because of the neoclassical production function. Okay, so what do I mean by that? Well, let's think about this. So when savings is greater than the amount we're losing, okay, then capital increases. Capital per worker increases. Okay? Now, when that increases, it also means that income increases, which is going to increase this left-hand side. Okay? So when y increases, this also means more savings. So it seems, kind of just thinking about it, that maybe there might not be this stability, right? Because when these two things aren't equal, it increases capital, which increases income, which increases savings. And so as a result, we're actually increasing this left-hand side here. And so kind of, just a priori, it doesn't necessarily have to be stable. And I have this here, and so this increase in savings means more capital, et cetera, et cetera. So kind of a priori, it doesn't have to be stable. Now, the reason it is stable is because of this declining marginal product of capital. And that's a feature of the neoclassical production function. It's a feature of the theory of the firm that we've worked on already. It's a feature of this marginalist theory of the firm. Okay? So because of this declining marginal product of capital, each additional unit of capital increases savings by less and less. So actually, although this left-hand side is increasing, it's increasing eventually slower than the right-hand side, which kind of increases 1 for 1 with increases in capital per worker. Okay, and again, this is a function of this declining marginal product of capital. So as I say here, this is because it increases y by less and less, and therefore savings also increase by less and less as capital increases, capital per worker. Here's what I mean, okay? You can see it here. Imagine we're currently in this state, at this level of capital. It leads capital to increase. But as capital increases, the amount of additional savings we get is smaller and smaller, right? The slope of this line is smaller and smaller. As we move along it, the additional savings is smaller and smaller. Whereas this part here is linear, right? The amount we're losing to population growth and depreciation is, just increasing linearly in K. And so it's because of this declining marginal product in capital that we're guaranteed a stable equilibrium, right? We're guaranteed to have these two lines eventually cross. And, to kind of prove my point, imagine we didn't have a neoclassical production function. Instead, imagine we had the following, that little y, or output per person, is just a linear function of K, A times K. Okay? What would that look like? Well, it would look like the following. Okay? Or sorry, here I have, Z. Anyways, you could think of Z and A as being the same thing. In any case, imagine this production function is just y equals A times K. So it's linear. Okay? So notice that this does not guarantee that these two lines eventually meet. They don't eventually cross. And so in this sense, there could be some, instability where here savings is greater than effective depreciation. That leads capital to increase. And as capital increases, there's nothing that's eventually bringing this amount of savings to be equal to the amount we lose each period to depreciation and population growth. Okay? If this function was curved, like the neoclassical production function, these two lines would eventually meet, and we would have a stable equilibrium. So in this case, if we have this non-neoclassical production function, there's no steady state value of little k. Okay, what if we wanted to draw a time series now of these variables? Okay, so we're returning now to the neoclassical production function. What would a time series of little k look like following this increase in the savings rate, little s? Well, it would look like this. So up until this point where s increases, k is stable. It's not changing, right? It's not increasing or decreasing. And this we saw. This is just the equilibrium. Okay? Suddenly, at this point here, this orange line, s increases. Okay? When that happens, remember that it leads capital per worker to start increasing. Because now that savings is greater than this effective depreciation, we start having an increase in the amount of capital. And then eventually this will slowly kind of converge to our new steady state value, k double star, at which point it will no longer be growing again. Same thing with y, with little y, right? Because little y is just this positive function of k, it's the same idea, right? Is that at this point where the savings rate increases, capital starts growing, and when capital starts growing, that is capital per worker starts growing. As capital per worker starts growing, then so does output per worker up until the point where we converge to our new steady state, where again, little y, output per worker is not growing, okay? Converge to our new equilibrium. Okay, next we're going to look at big K and big Y. But before I do that, here's a brief aside on growth rates, okay? I notice there's a lot of kind of derivations in math in this, and so here's another one, okay? And for those of you who have taken Eco 220, you should have seen this already. But if not, very simple. Okay, here's what it is. The derivative of the log of a variable with respect to time is just its growth rate, okay? So in other words, I'm going to show you that this on the left-hand side, so this is the derivative of the log of x with respect to time, is just the growth rate of x, okay? So here's why. So again, let's apply chain rule to this. So if we apply chain rule, remember that with log, we first take 1 over x, okay? So that's the derivative of ln x with respect to x. It's 1 over x. And then we take the derivative of x with respect to time. Okay, so this is the derivative of ln x with respect to x, and then derivative of x with respect to time. Just the chain rule, okay? Notice that we can change this. Derivative of x with respect to time is just dot x, okay? The change in x between any two periods, and then we're dividing by x, and so that's just the growth rate of x. Okay, pretty simple derivation. What's important here is that if I have a time series of the log, the natural log of a variable, okay, I take the log of a variable and then I plot its time series. The slope of that time series will be its growth rate. Okay, that's the same thing as what we see here, right? The derivative with respect to time of a time series is its slope. And here I have the log of that variable, okay? So therefore, the slope of a time series of log x is just g of x, or that is the growth rate of x. Okay, so with that in mind, let's plot the log of our variables, of our big variables, big K. So in particular, remember that K is growing at rate n initially, okay? So here's the log of K. So the slope of the log of K should just be n. Okay? Growing at rate n. Suddenly, S increases. The savings rate increases. And now suddenly K is going to be growing faster than n. Okay? And again, that's because suddenly capital per worker is growing. And if capital per worker is growing, that means that capital must be growing faster than population, faster than the number of workers. And that, again, keeps going until we get to our new steady state at which, again, we just have that big K, capital, is growing at rate n again, right? At the new steady state, capital is, again, growing at the same rate as population. And how do we know that? Well, because at the new steady state, little k isn't growing at all, right? And if little k isn't growing, that means that capital must be growing at the same rate as n, as population. And the growth path of y is exactly the same, right? For the same reasons we saw before. We know that in the steady state, y is growing at rate n, okay? Little n, the rate of growth of population. Then it will start growing faster as capital is growing faster. And then it once again levels off into its new steady state rate of growth, which again is n, okay, for the same argument we saw before.